And today we are having Kyriakos Destounis, who, well, just a very brief introduction. He did here his PhD, yeah. And afterwards he went on to do postdocs in Tübingen and Kremlin, Rome, correct?
Yes.
Okay. And now we're having him here to give a talk. So please go ahead.
Okay, thanks a lot, Alex, for the introduction. I see some old faces. I see many new faces. This is good. Group is changing, definitely bigger. So props to Victor with all his millions of videos that he's bringing around and bringing me here for a couple of weeks to discuss about the current state of the art of what I used to do in Tübingen, and now I'm doing with Paolo Panni, Federico Angeloni, a master student, and Massimo Baglio, a recently finished PhD student, so Dr. Massimo Baglio. Okay, so I'm going to be discussing supermassive rotating boson stars in extreme mass ratio inspirals. That's a fancy way of saying it. It's highly asymmetric binaries. I don't know. Andrea Marcel introduced that. I liked it. I stole it. And I'm going to basically be talking about transient resonances and how these can be imprinted in gravitational waves. All right. So, due to my dark nature, I would like to start with something called graveyard, and this is actually how they called it. So, I mean, I'm fine with it. Currently, we have a lot of events. Some come from electromagnetic observations, from stars and black holes from the Event Horizon Telescope, but mostly we have a lot of events from LIGO, Virgo, and kind of gravity collaboration, where we have at least 90, or approximately 90, or exactly 90, I'm not sure. Now, hidden in here, there are some weird mergers that I will be discussing later to give me the opportunity to introduce exotic compact objects. But for now, look at this beautiful thing. I mean, we have done 3 observation runs now, and we are increasing always the accuracy and precision somehow. And if we get lucky, as we get lucky with the first gravitational wave observation, which was the loudest to date, we may find more information about the underlying space-time that describes the final object, the previous 2 components of the binary, and so on and so forth. But we are humans and we want to evolve. We don't want to stay in this planet. We want to go to Mars. I saw today on the news that they are building some kind of experiment on how it would be to live in Mars, but on planet Earth. I don't know how they're going to do that. Elon Musk is the guy for that, but he's not giving the talk. So as we evolve, our detectors should evolve as well. And what is a better way of evolving our detectors is to take them away from this godforsaken planet that is full of noise. We have earthquakes. We have natural noises like earthquakes. We have anyway, anything has to do with the atmospheric noise and so on. But most importantly, we have humans on this planet, including all of us here. We're making noise right now. We are very close to the detector. The gravitational waves have like an amplitude of, let's say, 10 to the minus 20, 10 to the minus 23. They're very far away. They come from objects that are very far away. So we are so noisy that we want to take our detectors outside in space. And this is the next step. This is the laser interferometer space antenna, which is called LISA. And actually, I will have to give credit to other programs that may as well run together with LISA, or maybe a little bit later, which is Taichi and Tianqin. So this is, let's say, a doodle of what would the LISA detector look like. It has 3 spacecrafts. They send beams to each other. There's some special golden alloy inside that is playing the role of a test mass. It's spinning. It's going around the Earth in a particular distance from, it's going around the sun in a particular distance around the Earth. and a particular angle with respect to the sun, let's say. And right now we have narrowed it down, and this is the final proposal to have these laser beams travel a distance of 2.5 million kilometers, if I'm not mistaken. This is much larger than what we have with LIGO, Virgo, and Kerr. We're talking about some kilometers, not millions. So what does this mean? This means that we have more sensitivity. We should get cleaner signals. We can see new physics maybe, and we have a lot of targets to get this. By the way, Tianjin should be around the Earth or very close to the Earth. That would be weird, especially for astronomers that would be seeing the spacecraft and cursing, oh my God, here's a spacecraft passing by again. And Tahiti will be up front. So we cover just a little bit more of the observable universe. Okay, so this is essentially LISA. And the main things that you have to know about this talk. But one of the prime targets that I would like to talk about real quick is extreme acceleration inspirals, or these highly asymmetric binaries. These are just it's a binary of two compact objects, but instead of having equal mass like the ones that LIGO, Virgo, and Kerr are seeing gravitational waves from, they are comprised of a primary supermassive compact object. I'm not saying a black hole. I'm being very careful here. And the secondary stellar mass object. They usually originate either in dense stellar clusters or galactic cores. I prefer the galactic cores. They're quasars. We have seen orbits around some nothingness, like they gave the Nobel Prize in gravitational the Nobel Prize in physics very recently because of these orbits that they saw of these so-called S stars around something that we cannot see in the center of the galaxy. We have an image from electromagnetic observations, which is the plasma around the black hole. So the galactic cores are, for me, a better place to look at. The mass ratio, which determines an extreme mass ratio in spiral, spans from 10 to the minus 7 to 10 to the minus 4, depending on how you put the ratio, of course. It can be upside down. They generate gravitational waves in the frequency range of 10 to the minus 4 to 10 to the minus 1. So the detector peaks or peaks its sensitivity around the millihertz, where we haven't seen anything like that before, just because we don't have large distances in LIGO, Virgo, and Kerr for the lasers to travel back and forth. And because the primary object is so massive, it gives back this frequency. So essentially it dominates the frequency range because the secondary is nothing compared to the supermassive primary. They should perform after astrophysical capture around 10 to the 5 revolutions. We're talking about years of observation in the strong field regime. They will give us very rich waveform phenomenology, things that we maybe haven't seen before, or things that we have seen like in GR and then almost by theories of gravity are doing. But the most interesting thing about these objects is that the secondary is so small that it can basically trace the space-time geometry in a very exact manner, or at least almost exact manner. And as I said, they are prime targets of this triplet of future space-borne detectors. All right, now, how do we model EMRIs? People have been working a lot to understand this. So when we have two black holes that have equal mass, we can use post-Newtonian techniques if they are very far away. When they are coming very close to each other, close to the merger, we need to use numerical relativity, and after that we need to use perturbation theory because we assume that the the object that has formed is slightly perturbative until it relaxes to a stable state. Here we're talking about the inspiral stage, and we have a very tiny particle, let's say, or a point particle-like object moving around a supermassive object. Therefore, we can choose the supermassive object. In our case, the most general assumption could be a stationary and axisymmetric spacetime, similar to a Kerr black hole, like a rotating object that has this line element. And the secondary being so small at zero order in perturbation theory, we can assume that the short time scale follows geodesics. So something that we learned, actually something that you learned as physicists, is geodesics in classical field theory, classical mechanics. The geodesic equations have this form over dots denote differentiation with respect to proper time. This weird capital gamma here and all its indices are the Christoffel symbols of the spacetime, we assume. And instantly, either actually not directly from the geodesic equations, but from the Hamiltonian equations, or much easier from the Euler-Lagrange equations, we can find that stationarity, meaning that none of the metric tensor components depend on time, give us instantly a constant of motion when we're dealing with geodesics, not in spirals. So this is the energy over the mass of the secondary. Axis symmetry also gives us another constant of motion. It's the z component of the angular momentum. It has some particular form, and these have to be conserved throughout geodesic motion. Now, where I'm going with this, we have a spacetime with 4 degrees of freedom, T, R, theta, and V, and we are already having 2 conserved quantities. So we have 2 degrees of freedom. But there's also the conservation of the forward velocity of the particle, or equivalently the conservation of the Hamiltonian of the system, which depends on the mass of the secondary, which stays constant. Therefore, we have another equation. So now we go to 1 degree of freedom. We need one more to have what's called separability or integrability. By the way, this constraint equation is very helpful to understand when we have bound geodesic motion on a space-time with such a line element. Okay, so this effective potential is a Newtonian-like potential that tells us where we can start the geodesic, and if we start it inside this region, we will stay there forever, up to numerical equation. We'll never plunge because we don't include radiation reaction processes that change the energy and z component of angular momentum at this moment. Now, if we assume that the spacetime is Kerr, then we have the extremely likely Carter constant. The Carter constant is a separation constant. So imagine that these equations break down 4 equations. 2 of them become first order in E and V. And we have 2 other second order coupled differential equations for R and theta, for the radial and polar motion. If we have a 4th constant of motion, we can separate those 2, and then we have separability, or what some people in dynamical system theory call integrability. This means that we have 4 equations that are all first order and are decoupled, and we can solve them separately with appropriate initial conditions. This is very important for the discussion. So remember, if we have a Carter constant, then we have integrability. Or if we have any 4th constant of motion, we have integrability. It doesn't necessarily have to be Carter's constant. And the final thing, if we set this potential to 0, then we obtain the curve of zero velocity, as we call it, which basically defines the turning points of bound geodesics. So this is good if we're doing a short time scale revolution of 1, 2, 10, maximum 20 revolutions around the primary. But in principle, we have at some point to take into account the fact that the secondary has some mass, it has some structure, it's not a point particle, and it slowly but truly back reacts into the primary space-time metric. This is done with gravitational self force. This is a huge question mark for me, at least, because it's a really, really, really hard task that hasn't been completed yet. And what we essentially do, at least thematically, is putting a self force correction on the right-hand side, first, second, third, whatever order you choose. For example, in electromagnetism, we know the electromagnetic self force in any order. We know all the coefficients. So this is like we have an exact equation that describes everything. But for gravity, we don't. So these self force terms depend on the momenta. So the energy, the remaining momenta, the energy, the LZ, the R dot and theta dot, and the space-time perturbation. There's, as you can see, this traces back to the 90s and maybe even before that. And as I said, it's very complicated, very challenging. And only recently, and when I say recently, it's 2018, by Martin van der Ment, has been calculated for Kerr to first order in mass ratio. So we are very far away to have a complete gravitational self force description, even in Kerr. I'm not going to mention non-Kerr objects or bumpy spacetimes or anything that is not vacuum. Okay, so very hard. What do we do to avoid all that, or at least get some estimation of self force without actually calculating it because we don't know how? We take the adiabatic approximation, which is a very reasonable assumption made by Nino in 2003, where he said that essentially the change in the momenta is sufficiently small over a single orbit. Therefore, we can average the self force parts that we know from perturbation theory. But this is still not enough because it's still very hard. But in short time scales, the orbit neglects back reaction of the secondary, and on long time scales, the inspiral behaves like a flow through successive geodesics. So that's what adiabatic means, essentially. We are very slowly evolving closer and closer to the primary. Now, how we can move on and make things a little bit easier for us, because the adiabatic approximation is really fine, but you have to still calculate the average self force. The next step is a clad scheme. Now, clads means when you put two things together that they don't seem to fit, but somehow they work. And they call it the hybrid clad scheme, which approximates the fluxes of the momenta with post-Newtonian techniques. They have found some formulas back in 2006. Jonathan Gerg, Labevakis, Leo Barak, and collaborators in 2004, where they take these integrals, the average self force parts, and expand them in some post-Newtonian. When they do that, now they have some equations that depend on the orbital elements of the previous geodesics, and then you can actually perform inspirals with some accuracy. It's not perfect, but I'll show you later that it actually is quite good, at least for Kerr. Now, for the spacetime that I will be discussing, of course, it's not going to be Kerr. It's going to be boson stars. We know that boson stars have very different causal structure from Kerr spacetime, and essentially very different, at least at second post-Newtonian order mass quadrupole moment. Therefore, we will augment this second post-Newtonian formula with terms which represents the deformation of the non-Kerrness of the quadrupole moments, up to some order that we desire. And the order we desire is the second because it's the easiest one.
I would only the sympathy part.
Exactly. So forget about the conservative part. Here we are only driving the inspiral, but we don't take into account the conservative one, which is, let's say, if we go, like, we have a periapsis, apoapsis oscillation. When we go close to the object, the fluxes are larger. When we go away, they're smaller, and so on. So the conservative part through this clad scheme is taken out, which affects resonances in Kerr. But what I will show you now in non-Kerr, we can see that even without the conservative part, we have effects that mimic what happens in Kerr.
Well, my question is why should we care about highly extreme if we're leaving out some component of that?
Because we have no other way of doing so. When you're dealing with modified gravity, let's choose your favorite modified theory of gravity, which I'm sure you have none. Calculate the gravitational self force. Say to Martin, calculate the gravitational self force in first order for a rotating black hole in Einstein's scalar Gauss-Bonnet theory. He will quit. Okay, so it's not easy. That's why we do all this, and we leave some parts outside, which are essential for Kerr and essential for our case, but we simply cannot include them yet. There are some studies that they are trying to do so, and I'll discuss about this later.
What even for the second part, why don't you use like
Sorry?
even for the second part, you are using the approximation instead of like configuration for examining.
Yeah, because we don't want to solve the modified Tucholsky equation. I mean, it's even worse.
I think he's asking in GR, why are you including the terms and not doing
Because it's faster.
well, yeah.
No. There are studies where they use the hybrid clad sim or the analytical clads or any other clads that exist. They calculate the waveforms for L equals 2, L equals 4, whatever, like they add all these two components together, and then they compare with Tucholsky-based waveforms. They find overlap of 95%, and it's much faster. That's why they do this.
Okay.
But up to some periapsis, okay? After 5M, you are in danger of lowering your overlap a lot. So that's the reason behind why not Tucholsky or Reggie Wheeler if you have a Schwarzschild object or whatever. All right, now let's see some figures. Here I'm plotting a curve of zero velocity in black. It doesn't matter from which spacetime it comes from, but you can think of it as some sort of deformed curve, or even Schwarzschild has a similar curve of zero velocity. This is when we take the effective potential from the constraint equation that comes from the conservation of forward velocity, and you put it equal to 0. You plot it with respect to r and theta, and I have put two orbits inside. One that I call generic, actually anybody calls it generic, because it has all its turning points on the curve of zero velocity, and if you let it evolve for a sufficient amount of time, it will densely fill this box, or in a three-dimensional Cartesian coordinate representation, it will fill the torus, the three-dimensional torus. Okay? These generic orbits have a very irrational ratio of frequencies of r and theta. What is this omega r and theta? Basically, omega r are the frequency of oscillation between the periapsis and the apoapsis from left to right, the closer and the farther away, or perihelion, aphelion, I don't know, whatever you prefer. And the omega theta are longitudinal oscillations through the equatorial plane. Okay, so if you take the ratio of these two frequencies and it's irrational, then you have a generic orbit. But there are these special resonant orbits, or if you want to think about them as periodic, it's exactly the same. There are orbits that have a rational ratio of these two frequencies. What happens in this case? We have an orbit that is not space-filled, just does this forever and ever, as long as you can keep the accuracy and the precision of your simulation good enough. What does this mean? This means that it will start from some initial conditions. After some oscillations, revolution around the central object, it will go back to its initial state. And this particular one is a resonant orbit of 2/3. So it does 2 radial oscillations and 3 angular polar oscillations. All right. So the difference that we need to keep here is that generic orbits are space filling, and averaging the cell force makes sense, taking an integral all over the whole torus. But averaging these resonant orbits are problematic. This is when you need to use the conservative effects that we're discussing. Okay,
So, sorry, well, guys that know. This really just.
no, these are just geodesics. Just demonstration. You know, like I put an object on the center and I'm just showing the differences. Like even though I include the phi evolution here as well, there's some precision. It still looks quite resonant, especially if I plot it in a r theta plane. Now, why I am so obsessed with resonances, because EMRIs, as I said, evolved adiabatically. Therefore, we will experience them. If the secondary passes through a resonance, it will affect the orbit's evolution and the gravitational wave emission. That is obvious. Resonances are big because of the adiabatic nature of the ball. And if you see here in this depiction of a Kerr black hole, there's an innermost stable circular orbit, and see how many resonances, how strong they go with the pole, how thick they are. Where you can have 7/8, 2/3, the most important for me, 1/2, 3/5, and so on and so forth. This is a nice figure actually. So they occur, as I said, when 2 orbital frequencies form a commensurate or a rational ratio. It's the same thing. Even with phi, right? I'm just looking here at this kind of resonance, omega r over omega theta. It has been shown that even in Kerr, where we have integrability, they last for some dozens of cycles if you take into account pre and post resonant effects and the U. And this can lead to resonant kicks. So imagine the Carter constant evolving because of gravitational cell force evolution with the conservative and dissipative parts. And after resonance, the Carter constant does a very quick jump or drop exactly at the point of the resonance, which is really fun because we find, as I will show you, we will find exactly the same thing without even taking into account conservative effects. If we destroy a little bit the space-time, destroy in a sense, like make it more complicated. But they definitely impact parameter estimation. Okay, so an insightful way of understanding resonances, of course, is not making plots of a lot of orbits and trying to figure out which one of those is a resonant one and which one isn't, or calculating these frequencies. It's a time-consuming thing that we have to do. So there comes Poincaré with his many theorems and also the so-called Poincaré map. I would like to start from the bottom and go up. This is a generic orbit. It has some initial conditions that give you a generic orbit. You see a torus where the orbit lives, and it fills it densely as you evolve for more and more time. And then you put a surface of section, you cut this, whatever donut thing is, and you measure successive intersections. To make a Poincaré map, you need intersections on a particular surface of section of your choice that have a specific velocity. It has to be either positive or negative. It cannot be both, or else you are plotting two different Poincaré maps. And the intersection has to be perpendicular to the surface of section. Now you see that the intersections form some sort of circle. This is called the KAM curve, Kolmogorov-Arnold-Moser curve. It's very typical force factor for Kerr for any object that is integrable. Here, we don't care yet about integrability or non-integrability or any other effects that I will discuss later, okay? Now, change a little bit the initial condition. You see that these points start accumulating closer and closer to each other. Why? Because we are approaching slowly a perfect periodic orbit. This is a non-space filling periodic orbit. If I evolve this for much longer time, it will still give me a circle. If I evolve this for much longer time, it will still give me a circle, like here. But this one is a special orbit. This is the resonant orbit. And with the Poincaré map, you can spot those instantly. You see 3 dots. This is a 2/3 resonance that travels from point to point. Basically, all intersections at any time they happen in one of those 3 points. This is a good tool to understand if we're close or exactly at the resonance. Now, let's go back to darkness.
Sorry. How would the 43
The intersection points become more. For example, 2/3 means that we have multiplicity 2 and 3 dots. 4/7 means that we have multiplicity 4. We're gonna do 4 oscillations in the radial periapsis apoapsis and 7 dots. So the denominator of the resonance, the omega theta, defines how many dots we will have in
the
the point.
intersection is not enough. You need to look at the dots to know what that is.
Well, if you see, yeah, there's another aspect that helps us understand exactly what's the numerator. But for the denominator, a Poincaré map is enough. There's the rotation number that tells us that this is the exact resonance. For example, the rotation number, if you calculate it for this case, it's 2/3. It's 0.66666, and continue as many sixes as you want. It's actually amazing. The best resonance is satanic. Okay, so now let me motivate a little bit why I want to go to bumpy spacetimes and eventually to rotating boson stars. It's because of these peculiar mass gap events that we have found in 2019, 3 months in distance. The first one was of 2 kind of very massive black holes that form the most massive one that we have seen. It's 150 solar masses, the final object, and these ones belong to a region of mass that we were not expecting them to exist because of some sort of supernova instability. But other than that, they exist and they form a final object. So this is a peculiar event, and this gives motivation to people to think about, oh, maybe these 2 are not black holes, they're something else. And then we have 3 months later, another lower mass gap event where we have something here, as you see, if you can see, it's a question mark that merged with a black hole and gave a black hole. What the hell is this guy? We still don't know, and we have many conjectures and many different exotic compact objects about what this can be. It can be a very light, actually the lightest black hole or the heaviest neutron star, and anything else you can imagine. So this motivates this whole search for exotic compact objects. Now, the no-Kerr theorem dictates that heaviest physical compact objects have to be black holes. But because of these events that we cannot comprehend yet, we have started building a lot of so-called echoes. Actually, we started building those even before these events, of course. But yeah, now they are coming into play and they are actually helpful. And they lead to new physics always. We either need exotic matter, we maybe need to modify our gravity, we may just have to construct a bumpy model that has no theory on its back. It's just a line element with the attributes that we wanted to have. And in this nice figure that I stole from the thesis of Massimo Baglio, we can have boson stars, Procas stars, wormholes, black holes in scalar Kerr, which are essentially black holes surrounded by a boson star. You can have fuzzballs, gravastars, firewalls, whatever the hell is that. Okay, so there's a lot of exotic compact objects, right? And you either need exotic matter or extensions of gravity or combinations.
I have to correct you. The first thing is, what do you mean by the lower it only says that it's a black hole.
It has mass.
So it doesn't tell you that mass of people want to.
Maybe some uniqueness theorem.
Yeah, but the uniqueness only relates to the black hole. Not can't tell you if it's a black hole.
Yeah, maybe I stated the sentence wrong in the wrong way, but take it differently. Heavy astrophysical objects are supposed to be black holes, at least according to GR and in our knowledge. Yeah, it's not the no-Kerr theorem. Thanks for pointing that out, so I can take this thing out.
Okay. And actually, my second comment is about the diagram.
This
No. So why
dots.
we need so black holes in scalar area don't necessarily come in an extension of GR. We just need some matter.
Yeah, they can come from extension of GR and exotic matter at the same time. You see, there's some overlap in this. So it depends on how you model your echo. But the main point that I want to pass from this slide is that there's always an altered multipolar structure that affects binary evolution, gravitational evolution. We can never make an exotic compact object that has exactly the same multipolar structure as Kerr. Even if it has, let's say, the same mass quadrupole moment, the second or the next order will be different, and so on and so forth. So, what happens when we alter the multipolar structure? We have two theorems, we rule them all, as in ordinary theorems. And if we consider a weak perturbation to Kerr, so then let's take a Hamiltonian that has the Kerr Hamiltonian, which is perfectly integrable, and add a very small perturbation to it. So we have a Hamiltonian and an epsilon, which is much smaller than 1. Then we have two theorems that can dictate if we have chaotic effects or not, or if we have non-integrability or not. First is the Kolmogorov-Arnold-Moser, the KM theorem that I spoke about before, the KM curve, as I called it, which tells us that if the perturbation is non-integrable, actually, if the perturbation is integrable, nothing changes, everything is fine. We just smoothly deviate from curve, and that's it. But here, they state that if the perturbation is non-integrable, so it doesn't give us a Carter constant or a fourth constant of motion, then the dynamics smoothly depart from that of Kerr away from resonances. So even if we have non-integrability, and if we are far away from a periodic orbit, we may never see anything new besides some dephasing. But Poincaré and Birkhoff proved, and there's an actual inequality for that, I just don't put it here because it's too complicated, that close to resonances, we have a formation of a Birkhoff chain. Now, this could be a Poincaré map of an integrable system, any integrable system you choose. You have a central point, U0, which is a circular but otherwise planar orbit. It's not circular equatorial, or else you wouldn't cut the equatorial plane, because we always choose the surface of section to be the equatorial plane. And all the rest of the initial conditions for the orbit, for the geodesics, gives us these nice circles that we also saw before in the depiction of the periodic orbit and the generic orbit. But when the system is non-integrable and close to a resonance, remember that, we have a formation of this so-called Birkhoff chain, this ghoulish mesh that Lux Kyriakos and collaborators designed, but they come from all the papers, of course. What happens here exactly? We have a formation of islands of stability, as they call them, or resonant islands, where instead of the curve, this K-M curve, encapsulating the central fixed point of the Poincaré map, they encapsulate these black dots, which are the periodic stable points. This is where the resonance, the perfect resonance, lives. If I fine-tune my initial conditions, I will find only these three dots. Again, this is the 2/3 resonance. And around it, I will see islands that encapsulate that. This is what non-integrability does. Now, how this connects to chaos, it connects with these open circle points. These open circle points that live right between the edges of the resonant islands are points where chaotic orbits emanate, purely chaotic. But lucky for us, if the perturbation is small enough, they just form thin layers. This is just like an enlargement of the layer so that we understand that there are some chaotic layers around the island. Till now, I have either seen full-blown chaos, which is called a chaotic sea, like any initial condition you choose, you have chaos, chaotic orbits, random intersections in the surface section. But in this case, in the cases that I will present, at least for the bumpy spacetime, the layers will never be visible. I've never scanned the grid so finely to find them because they were irrelevant and I couldn't see them anywhere. And I've spoken with Kyriakos and other people, and this I'm going to show you for the first time that you can actually see a layer and not a chaotic sea. But this happens only for boson stars. Okay, now this is an actual Poincaré map calculated.
So we have some questions at the end.
Yeah. Okay, so this is a Poincaré map. You see that away from the resonances, nothing is happening, but close to resonances, the red one is the 2/3, the blue one is the 1/2. We have these islands of stability. If we zoom in here, we see that any blue curve encapsulates the central point. So this is a true Poincaré map. So what I want to share here and keep in mind is that the orbits inside the resonance, inside the island, share the same rational ratio of omega r over the omega theta. This doesn't happen in Kerr because we don't have an island, but this is actually amazing because now instead of having a zero volume point in the parameter space where a periodic orbit happens, we have a non-zero volume. Like we have some volume in the parameter space. By choosing a parameterized bumping black hole mimicker that started from Johansen, then we kind of destroyed it because Johansen wanted to make it look like Kerr, but without choosing a theory and having the maximum amount of deformations that keep all symmetries and attributes Kerr. We have made some nice figures that I will show you later. Essentially, this is one of the Johansen's parameter, this alpha Q2, that doesn't break integrability, right? Things are still integrable. This is only into play, but then we added this alpha Q, this red one, which controls integrability. And if it's non-zero, then there's no Carter constant or any other higher order, higher rank Killing tensor. Therefore, this would be the non-integral case. This goes back to Kerr if you kill the parameters, and the mass quadrupole moment C that is modified only by the non-integrable part of the perturbation. By the way, if you see he here and A here, this is the relation in dimension of the spin. Okay, let's plot the dissipative rotation curve. So the rotation curve is essentially the evolution of a rotation number, the evolution of the ratio of the frequencies of omega r over omega theta. For an integrable spacetime, the one that I just showed, the evolution is quite flat. It has no weird attributes. The same thing happens in Kerr exactly. And I went very close to the 2/3 resonance, and I didn't see any. Probably because I didn't include conservative effects, of course. This is only dissipative effects. But the non-integrable one gives us a plateau. What is this plateau? This is what happens when we are entering the island. So we enter the island and we have a fixed ratio of frequencies. And then we exit the island and things continue normally. The average time spent at the island is around 250 cycles, depending on the deformation we use, which is huge, without taking into account pre and after resonant effects. So we have a very huge effect at the orbital level, which can translate at the gravitational wave level. Sorry?
How does it depend on the mass ratio?
The mass ratio here is 10 to the minus 6, so you increase it, the months become larger. You decrease it, the months become days. I haven't checked that, but going from 10 to the minus 4 to 10 to the minus 7, I would expect just the time change, the time scales, because the mass ratio affects directly the fluxes, the post-Newtonian fluxes. I don't know if it's linear, I'm not sure. Now, to approximate the EMRIs really quick, we use the numerical platforms. We combine the exact particle trajectories we have found with approximate expressions for gravitational wave emission. This is what they call the quick and dirty EMRI waveforms, and it's perfectly suited for the phenomenology I want to show. And they, as I said, have remarkable agreement with the Polsky-based waveforms. Okay, that's why we're using it. This is the quadrable formula. This is the inspiral trajectory, this Z here, written in spherical coordinates at infinity. D is the luminosity distance between the source and the detector, the laser detector, and this is the incoming signal, which basically depends only on the inspiral trajectory. If we want to analyze the laser response, we have to take into account the antenna patterns, and then we have a waveform. We go to the Fourier domain, we break it down in short chunks with some offset. And what we see is that the integrable case, the evolution of frequency has nothing to show. It looks linear because it's only for 3 months. If I evolve this for a year, it will start going to the church. And here with white, we show just the waveform of one of the harmonics. This is the fundamental harmonic. But for the non-integrable case, we see a frequency modulation. We see what we call a glitch, but please don't confuse it with instrumental glitches, because this has an astrophysical meaning. It's the passage through the island that leads to this frequency modulation here, which drops from amplitude of 10 to almost 0, let's say 1 or 2 orders of magnitude drop. And then we have the formation of a peak, which corresponds to the frequency of the island, of the periodic stable point. And now I'm entering the boson stars, and over dealing with time, right? Oh, shit. Okay, now, why I want to study boson stars? Because I want to do something more realistic. The previous things were all somehow introductory, because we don't have a theory, okay? And these are hard games to play because you don't have the Kolsky equation or modify the Kolsky equation and so on. Here you can have one, but it's still really hard to work with it. So imagine a supermassive boson star that is rotating, that's why it looks like a donut, and a small object that we don't know what it is. It can be whatever. The motivation, I hope you all know, but I'm gonna go through it really quickly. It's a solution of GR with minimally coupled complex scalar field. It can be thought of as a large Bose-Einstein condensate. This was first proven by Ruffini. The caps lock is not a mistake. He loves putting his name in caps lock in his papers, even though the rest of the authors do not put them in caps lock. They are almost as compact as black holes, therefore they can mimic their gravitational wave emission. That's why they are interesting. They have no singularity, no event horizon, no surface, just a radius after which the complex scalar field decays to zero, exponentially. And may account for some percentage of dark matter at least. They can fix the rotation curves of galaxies that for right now they look very problematic. And bosons like scalar fields can explain also inflation. They are like 3 papers per day about inflation and how we can fix it by adding some scalar field. Finally, they have solid formation and stability mechanism. Okay, so very recently, actually, like 1 month or 2 months ago, not sure, Simonsen and William East, they started with initial data of 2 non-rotating boson stars, evolved them and formed a rotating boson star with full numerical relativity simulation. Now, as neutron stars have an equation of state that defines their maximum mass, so boson stars have a self-interaction potential. You can choose from all these 3, maybe there are more classes, but the most effective one to have massive or supermassive boson stars are this self-interaction potential when we have quartic coupling of the scalar field with gravity. To find the boson star solution, we solve the Einstein field equations together with the Klein-Gordon equation for the scalar field, but without the zero here, we have some derivatives of the effective potential we choose. And the particular Lagrangian of the self-interacting class is a kinetic term plus this self-interaction that I showed you before. Under stationarity and axisymmetry, we're looking for solutions of this form, and we essentially do the same thing in Kerr, but we are lucky enough to find something analytic. We try to find gamma, rho, alpha, and omega. We do this numerically by using Ryan's approximation, which tells us that if the coupling constant lambda is much larger than the mass of the complex scalar field, then the anisotropies at the energy moment potential are negligible, and we can assume a perfect fluid, which gives us easier solutions. To obtain solutions in quasi-isotropic coordinates, see Vaglio's paper, and Adelamassel's paper, and his thesis of Massimo. Now, thing to state here is that our boson stars don't suffer from any axisymmetric instabilities or origin instabilities or light ring instabilities. We have built 3 cases: a compact, less compact, less compact. Okay, and we have studied the EMRIs on those. These are the case and the parameters. We could go as far as 0.4 compactness, let's say, but we didn't do so because we're very close to the edge of these instabilities. And here I just show you, first of all, I show you the energy. This is the energy density, the cross-section of the energy density normalized with case 1. And you see that this one is more dense. You can actually spot the radius of the star. And as you decrease the compactness, then you get a larger configuration. This is the gravitational potential. Now I want to note here that because the rotating boson stars we have constructed for configuration 1 of this case 1, they don't have an event horizon but a boson star radius. These potentials URR and GTT that connect with GRR and GTT go to a constant. They don't go to infinity as in Kerr. Therefore, this justifies us just a little bit to use still the fluxes, even though we know it's not the perfect thing to do so, the post-Newtonian fluxes. So for supermassive rotating boson stars, we can plot the rotation curves. For reference, we have the curves, rotation curve, and then we have different compactness, different cases. This is the first case, second case, and third case. As you can see, the more we decrease the compactness, the more interesting things we get. First of all, we get a turning point. This is the most compact one, which looks similar to non-Kerr rotation curves. But since we can enter the star safely, we go up to the limit of bound orbits, to the edge of the curve of zero velocity. Decreasing the compactness makes this monotonistic change more obvious, which has been seen also in Kerr black hole with scalar Kerr. But interestingly, the interesting parts are these plateaus that appear because they are degenerate. If we zoom in, first of all, let's go to the case one, the most compact one. We have an island inside the star. It's fascinating, but nothing too crazy. And we have an inflection point here, which means we're passing right between two islands of stability. If, although I change the initial conditions, the initial velocity, in order to cross through the island, then I get again a plateau, which means that I will get something in the gravitational wave side. Case 3 is a clown. I mean, look at this. So many resonances. 2/3, 13/20, 5/8, 4/7. It's amazing. It has, again, this degenerate plateaus. And these are the zooms for the 5/8 and the 4/7. If I zoom in this region, which I did, you see a chaotic player forming. This is the first time I see anything like this. It's really interesting. There's a tiny island here, which is the 13/20. And if I put together all the plateaus and zoom in different regions, you will see that we have the 4/7, the 5/8 here, which I have to zoom in, the degenerate plateau, which means degenerate resonances inside and outside the star, and a thick chaotic layer up here at the inflection point. Now, these all three are for initial velocity 0, which is one part of the vector of initial conditions. But if I change it and put it 0.1 or 0.15 or whatever, then I can hit the plateau. I can cross through the island. And surprisingly, the island starts outside of the star and ends inside of the star. This is fascinating. I was expecting to see something great in the gravitational wave side. And now, if we turn on,
You could really finish.
yeah, it's 3 slides. So, if we turn on dissipation and cross through the 2/3 island, then we again see a plateau. No geodesics here. We're using a post-Newtonian fluxes. So this is a dissipative rotation curve for the case one. And it gives us typical glitches as we saw before, fundamental and first harmonic of the gravitational wave frequencies. Now, the 4/7 that lies inside also has a plateau. It has this non-linear now glitch. Non-linear because we are close to the plunge. Finally, the 2/3 huge island that starts from outside and goes inside gives this amazing and complicated representation of the gravitational wave glitch. The larger the gap is here, the more obvious it would be if Lisa finds something like that, that will have a problem with much filtering and parameter estimation. So to summarize, we are expecting to see thousands. I put a question mark because maybe we see 0 or thousands, depending on if they exist. We expect, though, I mean, I'm positive, kind of, to detect those with Lisa Taichi gently. Integrable deformations leads to smooth deviations from Kerr orbits and gravitational waves, but non-integrable perturbations lead to the formation of Birkhoff chains, which are imprinted in the gravitational waveform in the form of these frequency modulations / glitches. The events presented here, therefore, are smoking guns of non-integrability and chaos in EMRIs, which means that we need to take into account if we want to do proper parameter estimation, assuming, of course, that all these things exist, and even rotating boson stars. Now, the final thing is what we're trying to do is glitch waveform modeling which is definitely required because right now I'm just showing you phenomenology. We don't know exactly how to model those, but we know how to model somehow the Kerr transient resonances. And this is a work in progress with Alex Cardenas and from Princeton. Thanks a lot. Sorry.
If you enjoyed the video, like and subscribe.